Hello everybody, and welcome back to another geometry lesson. Today we're tackling 6.4, which is on the triangle midsegment theorem. So, first things first, I want us to start by drawing just any triangle. It can be equilateral, it can be scalene, isosceles, you can make it have acute angles, or right angles, or obtuse angles, whatever. But I want you to just draw a triangle right here. Now, here's the deal. I want to try and find where the middle of this triangle is, but not like the middle as a point. I want to make some sort of line that will cut my triangle directly in half. Sounds easy enough. We can probably estimate where cutting our triangle in half would go. The problem is getting it exact. It's really tough. Luckily, we have a method. We know how to find the midpoint if you knew two other points, right? Like if you know that A and B had, some number coordinates, you could use the midpoint formula to find exactly what's halfway between them. Similarly, we could do the same on another side, like A and C. If we found the midpoints of these two sides and connected them with a segment, that segment, believe it or not, will cut the entire triangle exactly in half. This segment right here that cuts the triangle in half is the midsegment of a triangle. So when we say the midsegment of a triangle, here's what we mean. A segment which connects the midpoints of two sides of a triangle. So, here's the idea for how to make a midpoint. To make a midsegment. Make a midpoint on two different sides of your triangle and connect it with a line. And you will get a midsegment. So, based on that definition here, I have an activity for us to try out. I want us to see if we can make all the different midsegments that are possible in this triangle. So, consider the scalene triangle. Decide how many midsegments this triangle has. Try drawing as many midsegments as you can, and then try and see what you notice about the shape created by those midsegments. So pause the video here, and in a second, I'm going to show you all of these midsegments. Hopefully you've had a chance to pause the video and try this one out. So to make a midsegment, again, we have to connect the midpoints of two different sides. So I'm going to start kind of like how I did my top triangle. I'm going to make the midpoints of two different sides and connect them. There's one midsegment. Well, these two sides can't be connected any more than they already are. This is connected. This is the midsegment. But there's a third side we have in this triangle, the side which goes across the bottom. Could I connect the left side and the bottom? Sure. And if we do, this is also a second midsegment of the triangle. And we can connect the right side and the bottom of the triangle too, making a third midsegment. In total, to connect all three sides of this triangle, we would need 3 midsegments to do it. The question now becomes, what do we notice about this shape created by the midsegments? I'm going to shade it in. You don't need to, but I'm going to shade it in so we can take a look and really see what this shape is. Well, it's definitely a triangle. That's one thing, but we want to be specific about it. Well, those of you who are observant may have noticed. Here's our original scalene triangle. It sort of looks like it's skewed off to the right-hand side. looks like somebody took a regular triangle and just pushed it over to the right a little bit. If I turn my paper upside down, this triangle here is also a scalene triangle pushed a little bit to the right-hand side. In fact, something that's interesting is the mid-segment triangle, which is the name of this. I want to call this mid-segment triangle. The mid-segment triangle is the same shape as the original. To call something the same shape, we're going to use the word similar. It's not congruent. Congruent means that they're the same size as well. They just are similar. It's smaller, but they're the same shape. The mid-segment triangle is the same shape as the original. Love it. Well, what else can we notice? Well, it looks like that isn't the only triangle that looks the same. These empty triangles here, plus this one, all look the same. In fact, it's 4 equal triangles that we've split the big one into. If we split our big triangle into 4 equal pieces, that means that any one of those tiny triangles, I'll use the mid-segment triangle as our example, it's going to be 1/4 the original area. Kind of cool, right? So that is what we can do with mid-segments. We can either just use one mid-segment, which you're going to see a lot of, or you can make all the mid-segments to make a mid-segment triangle. What we're going to do now is we're going to figure out what the triangle mid-segment theorem is. But I'm not just going to tell you the definition. No, I want us to prove the definition first. So what I have down here is this. We've got a big triangle, A, B, C, and a mid-segment, D, E. And there are 2 things I want us to do. In triangle ABC, we want to show that the mid-segment is parallel to side AC, and we want to show that the mid-segment is half the length of AC. So a little bit complicated. How do we do this? I'm not going to be too worried about B right now. I want to focus on just A. How can we show that 2 lines, specifically DE and AC, are parallel? Well, to show that 2 lines are parallel, they need to have the same slope, right? Luckily, we have a graph here, so we can find our slopes just by looking at it. If you don't have a graph, you might have to use the slope formula, which, as a reminder, is y2 minus y1 over x2 minus x1. But since we do, we can count out our slopes. We check how much up or down we go, and compare it to how much left or right we go. We make a ratio. Since we go up 3, our rise is 3, and to the right 2, our run is 2, the slope of DE is 3 over 2. Now, we can compare that to AC, which looks like it's a longer segment, but it doesn't mean the slope is different. If we take a look here, going from A up to where C is, we actually go up 6 spaces, and we go to the right 4 spaces. So the slope of AC is 6 over 4, which, hang on a second, that reduces to 3/2. These 2 slopes are the same, which means DE is parallel to AC. So line segment DE is parallel to line segment AC since their slopes are the same. Love it. All right, so that's one thing we can do here. Let's take a look at part B. We want to show that DE is half of AC, meaning we'll have to find the distance between D and E and the distance between A and C. You like how heavily I implied that we're going to use the distance formula? Because we are. The distance formula is the only real way we have to figure out how long these diagonal segments are. If they weren't diagonal, we could just count them. So, the distance formula is x2 minus x1 squared plus y2 minus y1 squared. In the past, I may have said y is first and then x is. It turns out it doesn't actually matter because they're both being added. And addition is commutative, which means you can flip them. So let's take a look here. To find the distance between D and E and AC, we're going to use these formulas. Of course, we are going to need to know the coordinates of D and E as well. So here's what I'd like you to do. Once again, you're going to pause the video. Step 1, find the coordinates of D and E. Step 2, plug them into the distance formula to find how long DE is. You're going to want it as a decimal, so you'll need your calculator. Finally, step 3, take a look and see if you can use the distance formula on line segment AC. Pause the video and give it a shot. Let's take a look together. First things first, let's check these coordinates. Coordinates of D are 0, -1, and E is at 2, 2. So, when we do the distance formula, we compare the x's, 2 minus 0, and compare the y's, 2 minus -1, and do some math. 2 minus 0 is 2, squared is 4. 2 minus -1 is 3, squared is 9. So what we're really trying to find is the square root of 13. When we estimate the square root of 13, again, you can do as many decimal points as you want. I'm going to cut off at 3.61. We repeat the process for AC. If we look at the x values of A and C, we can do 5 and 1 squared, then 0 and -6 squared. 5 minus 1 is 4, squared is 16. 0 minus -6 is 6, squared is 36. So we're trying to find the square root of 52. Well, the square root of 52 is around 7.61, or sorry, 7.21. Didn't mean to mislead you there. We need to ask, is DE half of AC? Well, you might be tempted to divide these two and go, no, because 7.61 divided by 7.21, messed up twice now, divided by 2 is 3.605. But remember that we rounded these two numbers. Without rounding, it would actually be exactly half. So we can say that DE does equal 1/2 AC. This is where we get into the triangle midsegment theorem. The triangle midsegment theorem actually has two pieces of vital information in it. Here's how it goes. The segment connecting the midpoints of two sides of a triangle. Again, this is just saying the midpoint in like a whole sentence instead of saying it in 2 words. Thank you, big ideas, very cool. The segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long, 1/2 the length of the third side. So this is very, very important. Let's look at our original triangle here. Since our midsegment connects AB and AC, these are the two sides. The third side would be BC. It's parallel to BC. Additionally, it's half the length. So if BC was 18, for instance, our midsegment here would be half of 18, which is 9. We can use this in a variety of ways, which we are going to be exploring on the next page. So let's take a look together at exercise 2. In triangle ABC, there exists a midsegment, DE, which is opposite to AC. We need to find the coordinates of line segment DE's endpoints, and we're given some coordinates. Something very important I want to discuss is this. There are some problems where when you draw a diagram, you don't want to mislead yourself, so it has to be picture perfect. But there are some problems where the diagram is just a tool to help us see what's going on. It doesn't do anything with the way we solve it. This is one of those problems where drawing a diagram will help us understand what's going on, but ultimately we don't need a diagram to solve this. We're just having to find the midpoints of certain vertices here. If you don't need a specific diagram, you can draw your triangle inaccurately. I have no idea if triangle ABC is an equilateral triangle, but I drew it that way. I have no idea if A is higher up than the other 2 points. In fact, between you and me, it isn't based on these coordinates. But I'm drawing it that way. I don't need it to be picture perfect. The only thing that does need to be perfect is this placement here. Line segment DE has to be opposite to line segment AC. If it's opposite to AC, that means it's parallel, which means the midsegment is going to be going in the same direction. If AC is going in this general direction, I'm going to put it right here. This is my midsegment DE. Mr. Strager, how do you know that D is in between A and B? I don't. Mr. Strager, how can you tell that it's going to be this orientation of a triangle? I don't. We are just trying to figure out the coordinates of these points. We don't need it to be picture perfect if we can do the math. So here's what we're going to do. We know the coordinates of A are at 1, 0, and B are at 3, 1. Shouldn't point D be right in the middle of these two, since it's the midpoint? So to find these coordinates, to find where D is, we can just do the midpoint formula again, like how we did last section. As a reminder, the midpoint formula is adding together our two x values and dividing by 2, then adding together our two y values and dividing by 2. So the two x values that are on either side of point D are 1 and 3, 0 and 1. That means that point D is at, well, 1 plus 3 is 4, divided by 2 is 2, 0 plus 1 is 1, divided by 2 is 1/2. The coordinates are 2, 1/2. That's D. Can you use the midpoint formula to find where point E is? Again, keep in mind that's going to be in between B and C. Pause the video and see if you can find the coordinates of point E. hopefully you've had a chance to try it out. Just to check your answers, the coordinates of point E are going to be 3.5, comma, -2. So that's how we find the coordinates of those endpoints. Exercise 3 tells us something interesting. Triangles are used in roof trusses due to their strength. Now, a roof truss is something that is used in constructing most roofs in America, actually. You might go past a house being under construction and you'll see a bunch of triangular shapes pointing at each other in the roof. This is because triangles are really good at holding their strength when they are supported. So, a roof truss is just another way of saying the inner construction of a roof. In this diagram, we see that line segment UV, which I'm marking here in purple, is congruent to line segment, or not is congruent to, sorry. It's a mid-segment though. We also see that VW, which I'm marking in green, is also mid-segment. And somehow we need to find the measurements of UV and RS. It's a lot. It's a lot to do. But we have some options. The thing is, we know that a mid-segment is going to be half the length of the opposite side. Aha. So UV is half the length of RT. Let's write that down. UV equals 1/2 RT, but RT is 90 inches. So UV is just going to be 1/2 of 90. The measurement of UV is 45 inches. Can we do something similar for finding length of RS? Again, pause the video. This will be a quick one, and see if you can find it. Let's take a look together. RS is notably directly opposite from VW. So VW is 57 inches. We can use that. If VW is supposed to be half the length of RS, and 57 is half the length of RS, to get RS by itself, we could just multiply both sides by 2. These cancel out, and 2 times 57 is 114. So RS is 114 inches. Very nicely done. Last question is the closest thing I can get to a word problem for this unit. You know, this unit is very conceptual, but there aren't a lot of long-form word problems. So let's take a look. In Michigan, each mile road is exactly 1 mile apart. Shocking, I know. I did a quick scan of the area, and I noticed something. Right up here is Birmingham, and I noticed that there was a triangle of roads formed right around where Birmingham and Royal Oak are. In fact, I did the math for you guys, and 14 Mile Road, the one that cuts right through the middle here, is a mid-segment of this triangle formed from Woodward, 13 Mile, and this residential street called Pierce Street. So here's the deal. We have a house on Pierce Street, and we want to make our way eventually to Crumble Cookies on 13 Mile and Woodward Avenue. Before we start, I want to mention these white bars that show the mileage shows the mileage of the entire segment. 0.7 miles is the distance from your house to Woodward Avenue, and 2.5 miles is this entire distance from Birmingham up here down to Crumble Cookies in Royal Oak down here. Here's the deal. We go on a bit of a journey to get to Crumble Cookies. I think it's an underestimation. We start by going north on Woodward to get our friend, then southeast to 14 Mile, then west back to our house to grab our purse. Afterwards, we go south to 13 Mile and east all the way to Crumble. So our journey looks like this. Step 1 is we go up here. Step 2 is we go down here. I know it's difficult to see, I'm sorry. There's so much ink on here that my pen is gliding right off. Step 3 is that we go all the way back to our house. Step 4, we go all the way south from our house down to 13 Mile. Step 5, we finally make our way over towards Crumbl Cookies. I want us to figure out how far we walked. In other words, I have to figure out how far each of these little distances are and then add them together. So pause the video and see if you can find the lengths of segment 1, segment 2, segment 3, segment 4, and segment 5, then add them together to find your total distance. Pause the video and try it out. This problem is very tough to do in order from 1 to 5. So let's start by filling out some things that we know. First off, we have the gimme here that segment 3 is 0.7 miles. So that's going to be a nice little break for us. But beyond there, we don't really have any other lengths given. Except we are told something in the words of the problem. In Michigan, each mile road is exactly 1 mile apart. That means between 13 Mile and 14 Mile is 1 mile. Wait a second, we walk that distance in segment 4. Segment 4 is 1 mile long. Okay, now we're making some progress. If we know that segment 4 is 1 mile long, what do we know about segment 1? From our home on Pierce Street to Woodward Avenue? Well, that also has to be 1 mile long. Why? Because the mid-segment cuts our triangle sides in half. So if this half is 1 mile, this top half is 1 mile. Segment 1 is 1 mile. Well, wait, we can use that same logic for segment 2. If 2.5 miles is this entire segment from up here to Crumbl Cookies, 14 Mile Road cuts that exactly in half. So what's half of 2.5? That's going to be 1.25. All these distances I should mention are accurate to satellite. Last, we need to figure out segment 5. We don't know much about segment 5. All we know is it's across from our midsegment. The triangle midsegment theorem says something about that, though. It says that these two are parallel to each other. That's nice, but it doesn't help us with distances. But it does say that the midsegment is half the distance of this long bottom segment. So if the midsegment is 0.7 miles, the bottom segment is double that. It's 1.4 miles. All we need to do now is add all these up together. When we do, we get 5.35 miles. A small price to pay for some good Crumbl cookies. Thank you so much, everybody. This lesson was not sponsored by Crumbl, but if Crumbl wants to sponsor me, I will gladly accept that. Have a fantastic rest of your night.